Hi, this is chapter 3 called the quantum theory and the electronic structure of atoms. So this is for me is an exciting chapter as a chemist, and I hope you get excited too as much. But as I told you guys before, this chapter is one of the, let's say, challenging chapter in chemistry. I would say even in physics also, the quantum theory discussed in both chemistry and physics as well. And if you are one of those students needing to take physics as well, um, you should feel blessed that you're taking this chemistry class. Before that, gives you the immense knowledge or inputs into the quantum chemistry that you can directly take and apply and feel a little bit more comfortable when you take the physics class. What you're seeing here, this is okay. What you're seeing here is the GIF image of sun, the sun, our star, traveling around the galaxy. The GIF image of it with its whole bunch of planets surrounding it at a speed of 450,000 miles per hour. The sun with that huge mass and huge planets around it is just taking all of it and traveling. Of course, each star in the galaxy would travel, in the universe would travel, so is our sun. So it is found to be that it is traveling at that speed, 450,000 miles per hour. Even with that speed, it's going to take thousands of billion years for sun to make a round trip around the galaxy. So I'm going to take an approach where appreciating quantum chemistry, how we, able to do the nice things that we are able to do by, showcasing some of those. Let's say, the difference between this generation that currently lives and maybe a century or 2 centuries ago is that we are enjoying enormous comfort compared to our previous generation. Like we can you can think about things like wireless communication, cell phones, use of cell phones, or maybe computers that we are using, or the internet, even to make it better, the computers and the microscopes that we could even see the DNA and edited DNA these days. And less popular things like you can make nuclear bomb and maybe actually the atomic clock. All of these things are kind of an application of the knowledge of the quantum chemistry or quantum physics. That's one thing that I want to highlight, like how useful it is. And also for this universe to exist and survive, everything is based on energy, and we just able to crack the energy and its potential once we study this quantum chemistry or quantum physics that we see. That's a brief introduction. So let me just give you a brief glimpse of what I'm going to discuss in this chapter. I'm going to start with the discussion on energy and energy changes. We're going to spend some time in this lecture. We are going to cover the first part. Then I'm going to discuss the nature of light, which is essential to learn for understanding of quantum chemistry. Then I'm going to build upon those topics of nature of light to quantum theory and Bohr's theory of hydrogen atom and wave properties of matter and the quantum mechanics. All of these are connected to nature of light. Once we do that, then I'll take you to understanding. So everything that we do here in the first 6 parts of this lecture is to understand the electronic structure of atom by studying the nature of light. We study energy and nature of light in the first 2 parts, and using that, we try to understand the electronic structure of atom. Remember in chapter 2 what we did? In chapter 2 what we did is we were able to identify that the smallest form of matter, atoms, has an area called nucleus, and inside an area there is a proton, neutrons, and outside an area there is an electron. That's all we know. And we mainly focused on neutrons and protons in chapter 2. we didn't really discuss much about the electrons over there. So in this chapter, we are going to discuss everything about the electrons, because to understand chemistry, you need to understand the electrons basically, because inside of the nucleus is nothing happening. It is, a stable portion of the matter. You cannot destroy it, you cannot change it. Atom is an atom, but you can change the electronic environment of the atom to make the things that you want the matter to do. So that is where the chapter is going to lead you to. In the first 6 parts, you're going to learn the you're going to lean into learn the electronic structure of the atom, which is the beautiful thing that you will see how each professor contributed and how we come up to the stage of saying like, oh, this is how an atom looks like. Inside of the nucleus, neutron and proton. Outside of the nucleus, electrons are arranged in a pattern that I'm going to reveal you as we are going to go through these first 6 parts. Once we do that, then it gets relatively easier from part 7 in this chapter, because it's not mathematical, it is abstract information, kind of like artistic. You kind of learn like outside of the nucleus how electrons arrange, and there is a pattern, and once you know it, and it's not too complicated. I will teach all of this information, or at least from part 8 to part 10 to my introductory classes as well, and everyone does great in those topics. So let me jump into the first part of this chapter. Okay, so the first part of this chapter says it is called energy and energy changes. Let me just define what is energy is, then jump into a little bit more discussion about history of energy, if I can. It sounds really odd when I say history of energy. I'm just trying to explain what I know and share some information that I know with you. So energy, as it states here, is the capacity to work or transfer heat. What is the capacity to work is, I have my cell phone here, I'm lifting this up, putting it in another place. What I did is I moved an object. So if you're able to move an object, it is a work. So I used energy to move object, my cell phone, from one place to another. Our transfer heat is, when, let's say, think of you have a hot coffee, you left it out. What happens eventually, it loses heat. So it is also transfer of energy, which is, from hot liquid to cold liquid, so that heat went out to universe. So this is also an energy. So these are the basic examples of energy. So what I'm going to do is I'm going to step back, and I'm going to step back from the chart. I'm going to visit the chart in just a couple of minutes. Before that, I'm just going to briefly talk about the origin, or what we know so far as a humankind. What we know is one, commonly we all know that before the Big Bang, right? That's what we read it in textbooks, right? So before the Big Bang theory, there is just unstable form of matter that is lying around. Apparently, it is called a state of singularity, where it is not interacting with anything. It is just energy, no matter form. There is a huge flow of energy in the entire universe that is singularly distributed. So apparently, in conditions matched, they all collide, and a Big Bang occurred. Like Big Bang is nothing like anything that we can imagine. Also, you can imagine like 1,000 trillion degrees Celsius temperature is released when all of that huge energy collide into each other. So when that huge collision of Big Bang occurred, that is when we call, that is like time 0 seconds. From then life started. From then, let's say, universe started. That's the birth of the universe that we call, right? So what happens is at that temperature, what universe did is there were byproducts of that Big Bang collision of that we can call it as just energy in the form of photons, or we can call them as Plancks now with the new terms that we added to it. That huge chunks of energy released. So that huge energy of huge temperature of Big Bang collision resulted in creating that once that huge high temperature is there, so it has to cool down, right? It cannot stay at that high temperature. When collision occurs, there's a friction temperature released, but eventually it has to cool down to smaller temperature relatively. So during those rapid cooling, that rapid cooling allowed for matter as we know it from in the form of universe right now, right? We call the matter anything that has mass and volume. That cooling helped after the Big Bang collision. It started cooling. That cooling helped creating the matter that we know in the universe. So although we don't know exactly what happened, but we can actually attest that during those collisions or at the fraction of a second of those collisions, the tiny form of matter particles started to form. Basically, protons and nucleus created and trying to attract at each other are confined into a small area. So they were called, we can say like this tiny nucleus were created, small nucleuses are created, and those nucleus were maybe after 1,000 years later, some thousands years later, started attracting electrons. And those nucleus created at the stage, initial stage, are mostly like hydrogen and helium without any electrons. Uh, that's why I'm just calling nucleus. They were naked nucleus created, hydrogen, helium, some carbon, some oxygen. Right? Even if you say sun, that's huge quantity, but relatively, these are the first four expected atoms that were created. So slowly, the electrons were started getting stuck to those nuclear particles of hydrogen, helium, carbon, oxygen, these. So when those electrons stuck to those nuclei, then the matter that we know as atoms formed. So when it happened, so about, let's say, I'm close to finish this story, I know a lot, right? I hope you're not getting bored about it, but it's something that we all need to know a little bit aware of, if not completely. So after about 1 billion years after Big Bang theory, so the gravity of these atoms, so all of these atoms are getting created, hydrogen, helium, carbon, oxygen, because the conditions match. Nucleus are getting attracted electrons, so atoms created. When atoms created, there are mass around now, right? So these all are gases. So individual molecules are gases. So when these huge clouds of gases everywhere in the universe, the gravity pulled all of these masses that are in the form of small chunks of gas molecules inside, like how you leave the ball up in the air, how it drops to the ground because of gravity. So gravity helped creating a mass that we know as now in the form of planets or stars. So gravity pulled all of those huge gas molecules and created galaxies. That is how galaxies created. So Big Bang created nucleus with protons and neutrons. Eventually electrons joined to create atoms. So those atoms were being formed and formed, created huge lumps of gas molecules. So those gas molecules combined with the dust particles are pulled into one large area by gravity called galaxies. That is when galaxies were created. So when that gravitational force created galaxies, then we have these stars, burning inside with the hydrogen, helium, all of these gases, fusion reactions. They eventually destroyed sometimes are, spit out forms of matter. So when these galaxies, the huge stars, let's say exploded, it creates new sun or new stars or planets. Like recently I read an article saying that sun actually has a twin star. So when sun is born, there is not just sun, actually there is another star as well that is somewhere in the universe now that astrophysicists are trying to find. That is how the star that we know, sun, that main source of energy for our planet, is created. That is how these planets that we are living on Earth is created. All of these as a result of starting with the energy that is flown around. Before Big Bang, in the state of singularity state, Big Bang occurred. Small nucleuses formed like hydrogen, helium, and they started attracting electrons, converting into atoms. Those atoms, found one form to be a meaningful, so much large quantity. Then it combined with the dust pulled by gravity to create galaxies. Inside the galaxies, we have these stars that burning, and sometimes they exploded. When they exploded, they create new stars or planets. We are one of those solar universe system. So we are under sun solar system now. So this is the story of what happened so far in the creation of Earth. So that we know, right? So one thing that we can say is, later I'm going to say, is all energy can neither be destroyed nor created. It only changes from one form to another. That is what we call it as law of conservation of mass theory. So everything that I talked about for last 5 to 10 minutes is basically conversion of one form of energy into another, but we are not saying it is created. It's already there. We are just changing it. We are just observing the changes of those energies. Okay, that's all you need to know about the energy to survive in this chemistry class, and also feel comfortable in physics class. So let me get back to the chart that you are seeing there. So we have many types of forms of energies, but in chemistry, there are two forms of energy that we really care. One is kinetic energy, and another one is potential energy. Kinetic energy, I'm going to show you the definitions again in next slide or the following slide. I'm just going to say it now. Potential energy is energy due to position. Let's say you can think like, this marker, if I drop it, it is going to go down to the land with some force because it is at higher position, right? So it can create some impact on the ground. If I have like, maybe marker is really light, to say that it can create an impact. That if I drop my heavy cell phone here, well, still light, but cell phone here on somebody's head, you can feel that, oh, it hits, right? Because it has some potential energy because I'm holding it high. So kinetic energy, opposite is, kinetic energy is as a result of motion, as a result of moving an object. Like if you punch someone, not an ideal example, if they feel that force, it is because of this kinetic energy, the movement that you are using. Or the better example is a quarterback throwing the ball. He uses his kinetic motion of the hand to throw the ball farther. The best one that can do the job is Patrick Mahomes, the Kansas City Chiefs quarterback. I like that guy. Now get back to chemistry. So kinetic energy and potential energy are convertible. Potential energy can be converted into kinetic energy can be converted into potential energy. The best example I can think right now is like if you visit any skate park, right? Skate park has these curved shapes, right? These curved shapes. So the skater can go up, and when he goes up, he is using kinetic energy to go to the top position like this. He stays there. He has the potential energy at the higher position, but he will come down with the use of potential energy from the high state to low state with that force of being a high side. So he will move to other directions. So that's the best example that you can see in real life, like how kinetic energy can easily convert to potential, and potential energy back to kinetic energy just by watching the skater skating in skate park. So there are types of kinetic energy that we can call thermal energy that we study extensively when we study thermochemistry later this year in the chemistry course. Other types of potential energy, again, we will discuss most of these in this term or next term as well. We can call them as chemical potential energy. So potential energy in chemistry is as a result of, I'm just using examples of cell phone because it is macroscopic daily life example, but When it comes to chemistry, the potential energy in molecules is like when a molecule make a bond, when an atom makes a bond with another atom, so it we say that it's like it has the potential energy. Like a good example to think is like if you have a dam on a river, if you open the gates, how fast water flows, right? Just like that, if you break a bond, then the energy comes out. Until you open the gates, energy, you don't see that it's high energy like water. You can just sense it, but once you open the gates, water flows really fast, right? Just like that. When you have a bond, it's like a dam between atoms. But once you break it, then you can see that potential energy. That's kind of like what we use, right? Like when you fill your car with gasoline, what you're hoping that is that the potential energy in the molecules as a result of bonding between atoms will break, and that you use it to run your car. That's an example of potential energy. You don't really have to worry about all of this. We spent like, exclusively like part of the chapter, a whole chapter just to discuss all of these. All right. Now let me get back to the actual topic. It's like everything that we discussed, so it's almost like 20 minutes since I start this part. So everything we discussed is to prime you up for this chapter, just an introduction. Just treat this as, friendly fireside chat or quantum chemistry. All right. Now let's get back to the topic of this chapter, the first part, energy and energy changes. A lot, right? No. So energy is the capacity to work or transfer heat, what we said. And also in the previous slide, we said that all forms of energy are either kinetic or potential, and they both can be interconverted. So what I'm going to do now is start defining kinetic energy and potential energy and give examples and see if you can quantify it using an equation. So example here is kinetic energy. Again, I said what I said about kinetic energy is the energy of motion. So you could actually calculate the kinetic energy using an equation which says that kinetic energy is equal to half mu squared. So m and u here is, sometimes people write like u, sometimes people write like v. In physics, they write like v. They both are same. U or v basically means velocity, and m is the mass. Units are important. We discuss that equation again in the next slide or the following slide. We will go over the units. And this part we already discussed. One form of kinetic energy of particular interest to chemists is thermal energy, which is like motion of the random motion of the molecules. As a result, heat transfers. That heat transfer you could actually calculate through experimentation, just by following the temperature changes. That's very easy to do. We discussed all of these thermal energy topics in chapter 10 called thermal energy. Right? So potential energy. So potential energy is energy possessed by an object by virtue of its position. We discussed some examples like holding something high and dropping it. The impact is because of how high or how low it is. It is because it has the potential energy. Or you can think of example as water held by a dam. So that is a potential energy because due to its position, it currently has high potential energy. So a couple of examples of potential energy are, one is chemical energy, and chemical energy is, we already discussed a little bit before, it's the energy stored within the structural unit of chemical substances. Like if you have a molecule, it has a chemical energy in it, and we call it as potential energy. The other types of potential energy is the electrostatic energy. So electrostatic energy is the potential energy results from interaction of charged particles, which is highly important. For an atom to exist, like we discussed in the previous chapter, chapter 2, you need to have the attractions between opposite charges of positively charged nucleus protons and negatively charged electrons that revolves around the nucleus. So those are happening as a result of electrostatic attraction. So we call that as electrostatic energy. And you can actually calculate electrostatic energy fairly easily using this equation called Q1 times Q2 over D, where Q1 and Q2 are basically charges and D is the distance between those charges. We will go over a problem to show how it works. So again, we are going to, this is the first chapter. We want you to have all the information that you need to have and get comfortable with what is an energy is. So we're just going over these kinetic and potential a couple more times. And I already slipped some of this information during my introduction. So I already said kinetic and potential energies are interconvertible. So because they were interconvertible, so it is easy to understand the law of conservation of energy, which says that the total energy of the universe is constant, because energy can neither be created nor destroyed, or you can call this law also as the first law of thermodynamics. So just an explanation: when one form of energy disappears, another it transfer. You can see it transferring into another form or appearing in the form of another, form of energy. Basically, law of conservation of energy. So as I promised before, we are just going to go into the units a little bit so that you would know what units to use. The SI, the standard international unit of energy, is Joule, named after a school teacher from Britain. He must be fantastic to come up with this as a just a school teacher. So he defined the Joule as the energy possessed by, the amount of energy possessed by 2 kilogram mass of a moving object at a speed of 1 meter per second. That's how it is defined. So if you use that definition of mass of 2 kilograms and the speed of 1 meter per second, you will find that energy will be 1 kilogram times meter square over second square, or you can simply say 1 joule. So these two, any one of them you could use without any difference. And also you can define the same joule in the form of Newton. Newton times the meter is equal to 1 joule. So the both are equal. So the joule of standard international is small. So you sometimes often have to end up converting your joule, which is really tiny amount, into kilojoules, so that the expression would look much more readable. So this is how you would convert a joule to kilojoule. 1 kilojoule is equal to 1000 joules. Just like grams. Like gram is small, kilogram is large, just like that. All right. Let's apply our knowledge on what we just learned about kinetic energy. Calculate the kinetic energy of a helium atom moving at a speed of 125 meters per second. All right. It is clearly asking what you want to do, which is calculate the kinetic energy. And it gave two types of information. It told you what type of atom it is and how much speed it is moving. Speed is important. Also, you need to have another information, mass. But it didn't directly give the mass, but it gave us a clue to identify the mass, which is helium. So helium must have some weight, right? Because it is a matter. It has mass and it occupies some volume. So we just need to identify what is the mass of helium atom is. Then we can apply our kinetic energy equation. E is equal to half mg square. So first you need to identify the mass of the helium. All we know is helium has the atomic mass unit of 4. The mass number of helium is 4, or to be specific, 4.003. It is measured in atomic mass units. But the problem is that the energy equation says that M should be in kilograms, right? That is how Joule defined the kinetic energy. Like in the example, like 2 kilograms mass moving at 1 meter per second. So, so first let's find a way to convert our mass of helium from 4 atomic mass units into kilograms. So we just need to have conversion factors. If you guys remember in the previous chapter, we discussed the weight of a proton or neutron in grams, which is about 1.661 times 10 to the power of 20 negative 24 grams. Each atomic weighs at each atomic mass unit weighs about 1.661 times 10 to the power of negative 24. So you can convert the atomic mass units into grams, and you can convert the grams into kilograms. I expect you to do this problem by yourself and look at the following answer. So if you do that, you will convert atomic mass units into grams, first conversion factor, and you convert grams into kilograms. Then you will have your mass of helium in kilograms. One helium atom is going to weigh about 6.6 times 10 to the power of negative 27 kilograms. Then you can use your equation, energy is equal to half mv squared. Half times the mass of the helium multiplied with the speed of the helium at which it is traveling to the power of square. Then if you do the math, you will end up with the kinetic energy of helium atom as 5.19 times 10 to the power of negative 23. That number negative 23 says that it's really tiny. It is understandable, like it says, whenever it says think about it, the book has some inputs to you to understand the information of the person. Because it's only a tiny atom and it has really low mass, even it is going at 125 meters per second, it still doesn't matter because of low mass. So you wouldn't see much of the kinetic energy for single element. All right. Let's look into another problem and finish this part of the lecture. So let's see, here we are going to go over how to identify electrostatic energy, a form of potential energy. Let's see if you can identify relationship between two different electrostatic energies. We already know how to calculate electrostatic energy. So the question is improvising a little bit. It is asking how much greater is attraction between charges of +2 and -2 than the attraction between charges of +1 and -1. The opposite charges are separated by the same distance. Okay. So distance is same, but the magnitude of charges are different. So what we are going to do is we are going to identify charges independently, and you can compare those numbers, or you can innovatively set up a whole +2 times -2 over d, and under denominator you can say +1 times -1 under d. You can cancel these and come up with the ratio. All right. Now let's look into that. Let's identify both the electrostatic energies for E2E +2 and -2 and E +1 and -1. So you would end up with these electrostatic energies of -2 and -1. And this is independently, but if you want to compare how one attraction is greater than another, then say if you have charges of +2 and -2, you can compare them by taking the ratio of +2 and -2 over d over +1 and -1 over d. So if you do that, you cancel the d's and you will end up with a number of 4. What it says that is that the attraction between +2 and -2 charges is about 4 times larger than the attractions between +1 and -1 charges. This is all for this part 1 of the lecture. As I warned you, chapter 3 is hard, challenging, and long, but it is worthy of your time, and you will add plenty of knowledge to your arsenal at the end of these lectures. So just stick with it. I'm trying to do my best to make this material more presentable to you and present in a way that you will understand it much more easily. That's why sometimes I might take a little bit longer time in these lectures, just to make sure that you get these, just to make sure that I get the point that I want to get it to you across easily. All right, I'll see you in part 2 of the lecture.